Hello students, guess who this is? Correct, it's your professor Dr. Mink, and welcome to another exciting lecture for CompSci 2 CSE 223. We're now moving into the content for chapter 19 from your textbook, which is trees. Let's get started. You should be used to this format by now. The scope of this chapter includes discussion on trees as data structures. We'll cover the terminology related to trees, implementation of trees, then we'll analyze tree efficiencies, tree traversals, say that 10 times quickly, and we'll end the discussion with expression trees. A tree is a fairly complex nonlinear data structure in which elements are organized in a hierarchy. A tree is made up of nodes and edges. Nodes are where elements are stored, and edges provide the connection or linkage from one node to another. Each node is located on a particular level that speaks to the hierarchy of the tree, and there's only one root node in the tree. Nodes at the lower level of a tree are children of nodes at the previous level. But remember, there can only be one root node. And a node can only have one parent. However, may have multiple children. Siblings are nodes that have the same parent. And the root node is the only node that can't have any parents. Obviously, it's at the top of the hierarchy. There's some more terminology and definitions for you. A node with no children is referred to as a leaf node. And a node that is not the root, but has at least one child, is an internal node, which means it has a parent and a child. A subtree is a tree structure that makes up part of another tree. And we can follow a path through a tree from a parent to a child starting at the root. A node is an ancestor of another node if it is above it on the path from the root. And when I say path, you think about, well, we're going to look at a hierarchy, a tree structure next, but think about starting on this structure. It's going to be depicted graphically from the top to the bottom. In this structure, this tree, you see examples of some of the terms we just covered. Obviously, A is the root. B is an internal node, which means it has a parent, children, tree structure beneath it. And then K and P, in this example, are leaves. They do not have any children. Nodes that we can reach by following a path from a particular node above it are descendants of that node. And the level of a node is the length of the path from the root to that particular node. This is really important to understand, and we'll go over this graphically. The path length is the number of edges followed to get from the root to the node. And the height of a tree is the length of the longest path from the root to a leaf. And remember, a leaf is a node with no children. I find it much easier to understand this visually. In the graphic depiction here, we have 4 levels of this tree. Level 0 is always where the root node is. It's the beginning. We have level 1, A and B. I'm sorry, B and C. C is a leaf. B has children and a tree beneath it. D and E, F and G. And F and G are leaves. There are multiple ways that trees can be classified. One of the more important criterion is the maximum number of children any node in the tree may have. And that's referred to as the order of the tree. General trees do not have a limit to the number of children any particular node can have. However, a tree that limits each node to no more than n children is referred to as an n-ary tree. Next up, let's discuss balanced trees. Binary trees are trees where or in which nodes will not have more than 2 children. And a tree is balanced if all of the leaves of the tree are on the same level or within 1 level of each other. In this diagram, you see a balanced tree on the left, and that has levels 0, 1, and 2, and an unbalanced tree which has leaves on different levels. So that has leaves on 0, 1, 2, 3, and level 1. If you've been paying attention, you could probably see where we're going with this line of thought. Let's talk about full and complete trees. So a balanced tree with m elements will have a height of log sub n of m. A balanced binary tree with n nodes has a height of log sub 2 of n. An n-ary tree n-ary tree is full of leaves if all the leaves are at the same height. Remember, a leaf is a node with no children. So it's full if all of the leaves are at the same height. And then we're going to take a look at a graphic depiction of this in a second. So just hang on to that thought. And a tree is complete if it's full, or full to the next to last level with all leaves at the bottom level on the left side of the tree. We're going to now take a look at a graphic depiction of some full and complete trees. Now, while looking at this diagram, let's restate some facts from the previous slide. All 3 of these trees are complete. Just to reiterate, a tree is complete if it's full or full to the next to last level with all leaves at the bottom level on the left side of the tree. So A is full to the next to last level with all trees at the bottom level on the left side of the tree. So is B, and so is C. So all 3 are complete trees, but only tree C is full. An n-ary tree is full if all leaves of the tree, leaves are nodes with no children, if all leaves of the tree are at the same height and every non-leaf node has exactly n children. And only tree C fits that criteria. So what does it mean to say that the height of a complete binary tree is O of log n? Let's revisit binary search. Binary search is an example with complexity O of log n. So let's say that nodes in the bottom level of the tree here represent items in some sorted collection. Binary search, if you recall, is a divide and conquer algorithm, and the drawing shows how we will need at most 4 comparisons to find the record we're searching for in this 16-item data set. This is obviously a binary tree in that each level contains double the number of nodes compared to the level above. It's also a complete and full tree. Hopefully, you can see that when implementing trees, a linked list structure or a linked structure is an obvious choice for implementing these trees. Array-based implementations, less obvious, but can be somewhat useful. First, we're going to look at the strategy behind a 2-array based implementation. We can use an array to represent a tree for full or complete binary trees. So, for any element stored in position n, the element's left child is stored in array position 2n plus 1, and the element's right child is stored in array position 2 times n plus 1. To represent a tree is not complete or relatively complete, this approach wastes large amounts of array space and would be better implemented with a linked structure. So let's review how the children are stored using an array. Just to reiterate, if we have an element, let's focus on B. Okay. We can start with A if you want. A is at 0, so the left child of A is stored at 2n plus 1, which is 0 plus 1, which is 1. So there's B in position 1 in the array. So now let's look at B and its 2 children, D and E. The left child of B, which is stored at 1, is going to be 2 times 1 plus 1, so it's going to be 3. So D is already at 3. The right child is 2 times n plus 1, which is going to be 4, and there's E at 4. And you could see that C is stored right next to B because it is on the same level as B. So you need to make the space for these. And as you go down additional levels, you'll be increasing the index number, and thus the children, especially the children, the right children, will be further away. And you could see that this still leaves some open space. What would that open space be for? Well, what if C had children? Okay, especially the left children. So take a close look at this if you want to back up to the placement rules, the computed child links in the previous slide. Feel free to do so. When using an array for a tree as the underlying structure for a tree, each element of the array is an object, and that object stores a reference to the tree element, and the array index of each child that object has. This approach simulates the way operating systems manage memory. In other words, array positions get allocated on a first come, first served basis. Here's a graphic depiction of simulated child links. If you remember what was said previously, each element of the array, such as A, B, C, D, E, and F in this graphic depiction, each of those is an object, and that object stores a reference to the tree element and the array index of each child. So you can see A holds a reference to C and a reference to B. B holds a reference to E and a reference to D, and so on and so on. So, as covered in great detail, the process of iterating through the elements in a linear structure is very straightforward. You either go forward or backwards. For nonlinear structures, including a tree, the possibilities are more complex. We're going to look at 4 ways of traversing the nodes of a tree. These are called traversals, and they all start at the root of the tree. And each node can be thought of as a root of a subtree. Here's our first look at the 4 methods of traversing a tree. First one is preorder. Start at the root, then you traverse the subtrees from left to right. In order, traverses the left subtree, then visits the root, then traverses the right subtree. And remember, each node can be considered a root with a subtree. Post order traverses the subtrees from left to right, then visits the root. Level order visits each node at each level of the tree, from top, the root, to bottom, and left to right. Now let's review the 4 tree traversal methods we just discussed on the previous slide with a graphic depiction of a tree that you see on this slide. So if we were using the preorder method, which I'll review, you visit the root, then you traverse the subtrees from left to right. The order of the traversal would be A, B, D, E, and then C. In order, traverses the left subtree, then visits the root, then traverses the right subtree. So in order would be D, B, E, A, then C. Post order, which traverses the subtrees from left to right, then visits the root, would be D, E, B, C, and then A. And then level order visits each node at each level of the tree from the top, which is the root, to the bottom, would be A, B, C, D, E. Obviously, well, hopefully you can see where we're going with this. Recursion greatly simplifies any implementation of a tree traversal. So for example, here's some pseudocode for preorder. Visit the node, traverse left child, traverse right child. In order, traverse left child, visit a node, traverse right child. Post order, traverse left child, traverse right child, visit node. A level order traversal gets a little bit more complicated and involves the use of extra structures such as a queue and or a list in order to create the necessary order. Obviously, we're going to demonstrate, implement all of these. So stay tuned. I think it's about time for a demo. Remember, a binary tree, each node can have at most 2 children. This is a binary tree. And I have a program that I've created. It's a little bit less complex than the one that comes with the textbook to get us started on this topic. So here is a run from that program, and I'm going to show you the program and we'll watch it build this tree, but I thought it would be useful to see a graphic depiction. So in this example, we start off with building a tree that has a root value of 5. And then we insert 2 to the left of 5. And then we insert 4 to the right of 2, 8 to the right of 5, 6 to the left of 8, 7 to the right of 6, 3 to the left of 4, and 9 to the right of 8. And then we're going to have a method that traverses the tree in order and post order. And in order will yield the values 2, 3, 4, 5, 6, 7, 8, 9. Post order will yield 3, 4, 2, 7, 6, 9, 8, and then 5. You could probably detect an assignment bubbling to the top, bubbling to the surface of my mind. But let's not go there yet. Here we have a program run from the binary tree program that I promise I will show you. I've said that twice so far. And I drew the best I could. I'm not an artist. I drew the tree to the left of the run. And then I've also added the in order and post order recursive sequences. Sorry for that cat in the background. Can't catch a break here today. So anyway, I want you to remember that lowercase a in ASCII and Unicode carries a greater numeric value than uppercase a. And in the program, the children are added to nodes based upon their equivalence or comparison, less than, equivalent, or greater than the node. So you'll see all the lowercase characters. Obviously I did this with chars instead of ints, as we looked at in the previous example. All the lowercase chars are on the right hand side of the root A, and the uppercase chars are on the left side. And so, and you could even look at the node lowercase h. E is to the left because E is has a lower numeric value than H. It precedes it in the alphabetic sequence, and I comes after it. So I've also included the recursive in order and post order sequences in the lower left hand corner of this slide for you to take a look at. And I promise you I will show you the code next, or in a very short period of time. Here's your first look at my tree demo program, and it simply works on a series of nodes. So I've got my tree class, and then I've got my node class, which basically has a value for char, and then nodes. It creates the nodes for left and right, and sets them to null. And here is the here's the method that does the bulk of the work. It inserts a new node based upon the comparison of the existing node. So you pass a node, you pass a character value. If the value is less than or equal to the value of the node, in this case we're using chars, it inserts it to the left or it inserts it to the right. And then here's my in order traversal, which I've already shown you. It's a recursive traversal. So I've run this. I can run it now. Oh, let me show you the code I put in the main to insert all those values. And then we call the traverse in order method and the traverse post order method. Take a close look at this, back up, look at the tree that it's created and the order of the traversals, because I am going to assess you on this. As a matter of fact, the gears are really turning in my mind right now as to what is the next assignment or next project that I'll have you do that will assess your understanding of this. So here we go, students. I've made up my mind. Here is your assignment. You're going to take the program we just looked at and the tree that I have here on this slide, and you're going to write the pre-order and the level order traversal methods for this tree. Take a good look at this example I've given you here that shows the pre-order, in-order, post-order, and level order traversals of a tree. And here's the tree we're going to be using. And I'll give you the source code for most of what I've shown you already. And here is your last significant hint for the tree traversal project, which is project 1 for chapter 19. Here you can see a run in which I have 4 methods, 4 traversal methods: in order, post order, level order. I also have a method called height, which calculates the height, which is necessary for level order. And then I've got the pre-order traversal. And here is some starter code for you. And here is the representation of the tree as I created. It's a more balanced tree than the binary tree I used in the first example. Don't forget to ask any questions, and don't wait till Sunday night when it's due. Take care. Next topic on the agenda is we're going to look at an interface for a binary tree ADT. Here are the operations that the interface will have. You can see get root, returns a reference to the root, obviously. Is empty, we know what is empty does. Size, number of elements in the tree. Contains, this is a new one, determines whether or not a specified target is housed or contained in the tree. Find returns a reference to the specified target element if it is found. ToString, iterator in order, iterator pre-order, iterator post-order, and iterator level order will return an iterator for an in-order traversal of the tree. And finally here, we have a UML description of the binary tree ADT interface and each of the methods we'll need to implement to make this work. I'm not quite ready to show you the code in Java yet, in a project. So let's review the binary tree ADT interface. You could see the use of the generic T, and we're going to import. This interface is going to have an import to the java.util_iterator library. And so the first method we see referenced is getRootElement, and it returns a T or whatever the data type is. We've got isEmpty, which returns a Boolean. Next, within the same interface, we have size, which returns an integer, return the number of elements in the tree. We have contains, which has a parameter of the target element, which is type T, generic, and it returns a Boolean. It will return true if the target element is contained within the tree. And then we have the find method, which returns the actual returns an actual element, T. Moving right along, excuse me, we have reference to the string method. ToString method, which returns a string representation of the binary tree. And then we have the iterator, which returns an iterator over the elements of this tree. Then we have another iterator for the iterator in order, and one for iterator pre-order. And then finally, we have our last two elements of this interface. That's the iterator post-order and the iterator level order methods, which return an iterator. A specific example or type of tree is an expression tree. And that shows a relationship among operators and operands in an expression. And this type of tree, the expression tree, is evaluated from the bottom up. So in the diagram on this slide, that tree depicts 5 minus 3 times 4 plus 9. We're now going to take a look at an expression tree created from a postfix expression. It will, and this is an array-based tree, and it will use the operands and operators from a postfix expression along with the tree to evaluate the total postfix expression. It's a modification of an earlier solution that we use, and it uses, as I mentioned earlier, it uses a stack of expression trees to build the complete expression tree. Now I have a demo coming up, live demo. Well, I guess it won't be live. I'll be recording it live and you'll be watching it not live. Anyway, let's move on. First, I'm going to walk you through a demonstration on how a postfix expression is evaluated using a tree based upon a stack. So the postfix expression in this example is 5 space 3 space minus space 4 space asterisk space 9 space plus. So the way these work is 5, 3 are the operands for a binary operation. In this case, it's going to be subtraction. So 5 will be pushed onto the expression tree, and then 3 will be pushed onto the expression tree, and then we will see an operand. So we'll create a new expression tree, but the operation will be minus. So we'll push a new expression tree minus op1, op2. The root will be minus op1, op2 will be children. And what that will do is that will evaluate 5 minus 3. We'll push a new expression tree 4, null, null. Then we will get another operator, and then the expression tree will look like 1, 2, 3, 4, 5 down, row 5, column 3. So you've got a root, which is the asterisk, children minus 4, and then children of the minus as a root 5 and 3. And then we will push new expression tree 9, null, null. And then we will push a new expression tree plus op1, op2. And this expression tree will ultimately be evaluated to, let me see, looks like 17 will be the result of this expression tree. This is not the expression tree, I'm sorry, this is not the postfix expression, pardon me, that I'm going to use in the demo next. Okay, students, this is probably going to be your most challenging assignment. Did I mention this is an assignment announcement? Yes, that's what it is. So we've talked about trees and we've talked about expression trees. Here is an expression tree that evaluates postfix expressions. And I'll actually start off by running it. Here's a run I just had, but I'll run it. And I'm going to show you some hints, but I'm going to leave a lot of details out for you. Here's the driver program with the main in it, and all it does is get things started, really. Here's what you're going to have to create, the postfix evaluator. I just happen to call mine 3 because it took me 3 attempts to get it into the format I wanted for this assignment. And here you'll see the members of the postfix evaluator 3 class. I'm going to run this and show you how this works. So this has, by the way, it has the linked list infrastructure and the stack ADT class. So this is something, this is all stuff that you've done before, and I'll give you the exceptions it throws, but I really want you to implement this postfix evaluator as it's currently structured. So, and there's actually some extra credit available here. So what this does is it takes integers and it will push them onto a stack until it sees an operand. I'm sorry, an operation. So in this instance, it's going to push a 4, it's going to push a 5, and then it's going to recognize the next token, and just hold that term for a second, as an operation. So it will then pop off the 4 and the 5, perform the operation, and push the result back on there. So then I'm going to take, let's just do 10, 10 multiplication. So this will come up with 4 times 5, 20, 10 times 10, 100. So we'll have 20 and 100 on the stack. And then we'll just simply add. It will pop off the 100 and the 20, and it will evaluate the expression. So some things that the postfix evaluator uses. It uses the tokenizer class, and I want to just talk about that right here. The tokenizer class takes a string, a long string, an expression. That doesn't have to be a long string. And it creates a tokenizer object and a string tokenizer object. And that allows us to use that as a series of tokens. A token is an example is an element within a string, specific element. In this case, the tokens are either operands or operations. Operand being 1, 10, 50, 100, or an operation being an asterisk, multiplication, slash division, plus addition, minus subtraction. Okay, so I'm going to just give you some hints, right? Okay, is the token an operator? If it is, it's going to pop. These are all binary operations. They require 2 operands. It's going to pop, and then it's going to evaluate the operation, and there's the extent of the hints I'm going to give you. Now, I think I'm going to run this in debug mode with some breakpoints next. I don't have that set up, so let me pause and get that set up just so that you can see how operands are pushed and popped off the stack during the running of this application. So let's hold on. Okay, so I've placed breakpoints at 2 places in the postfix evaluator class, and those breakpoints correspond to identification of an operator and then popping the last 2 elements off the stack and performing the operation of pushing the result back. And the other one is identification of a new integer operand being encountered in the tokenized string. So I'm going to I'm in the middle of running this, okay, and I will, it's asking for, oops, postfix expression. We'll just do 3 and 4, and we'll multiply them, and then we'll do 2 and 7, and we'll multiply them, and then we'll add. So that's going to give us 12 and 14, and that should give us 26. So here we are at the breakpoints, and I just want to show you the data. So first breakpoint, the stack is empty. Okay, we've got our tokenizer object, and the first token is that 3. Okay, remember 3 was the first token in the string tokenized string expression. So we've parsed 3 into an integer, or we will parse 3 into an integer as we move forward. Stack is empty, so if I now move forward and look at my variables, okay, so now my next, let's get to my next token. I now have a 3 pushed on the top of the stack. I'm looking for my next token. I'm doing this blindly because I can't see the code. I'm stepping. Here it is. My next token is 4. So we now have a second operand that will be pushed onto the stack. Now notice the top, right? Next is null, and the top holds an element that's 3. Okay, so let's move forward. Okay, now the top holds a value 4. Next is not null because next now holds an element 3. So 3 is next, top is 4, as you would expect in a LIFO protocol stack. And so let's move forward a little further. I'm looking for my next token. My next token is an asterisk, which is an operator, not an operand. So this is going to signal or generate a different path. It's now going to look at this as an operation that needs to be performed, a binary operation with 2 operands. So it will pop off op2 is 4, op1 is 3. If we look at the stack at this point in time, the stack is empty. The top is null. Okay, so we're about to perform that operation, which was multiplication. There's our result, 12. And 12 is now on the stack as top. If you recall, here's the original expression, postfix expression. We're going to push a 2, push a 7, so there'll be 7, 2, and 12 on the top, next, and next. By the time we get to the next, there's our 2, there's our 7. Okay, now if I look at the stack, let's see what's on the top. Top is a 7. Next is an element 2. Right, there it is. And then next is an element 12. So we have a 7, a 2, and then underneath that, if you want to use that terminology, is the result of the original 3 times 4 operation. Now, there's op 2, there's op 1. Here's our result, 14. Now at this point, the stack only has one element. It has the 12 on there. It popped the 7 and the 2 off, and it's about to push the result back on this expression tree. Okay. The value at top is 14. Next is 12. See it? There's the 12 was pushed. There's the 14 was pushed. We're now going to get another token that is, there it is, multiplication. It will now pop the 14 into op2. It will pop the 12 into op1. And at this point in time, the stack is empty. Look. There's our result, 26. 26 on the top of the stack. When it gets to no more operands, we're about to end. And we're done. And there's our output. We're not done, actually. The program is asking me if I want to continue, but now main ends. So you're going to write the postfix evaluator, and I will give you extra credit if you add exponent as an operator, which is going to be very difficult. Here we have the UML diagram showing the relationship between all the various classes and the interface for the project we just discussed. Another type of decision tree is a tree where the nodes represent decision points. These are also used in expert systems, automated expert systems. And each of the nodes is a decision point, and the children of those nodes represent the options available. The leaves of a decision tree are the possible conclusions that may be drawn based upon the path taken. A simple decision tree with yes and no questions can be modeled using a binary tree. These are very useful in diagnostic situations, medical, car repair, etc. Obviously, we're going to take a look at a decision tree. Here we have a graphic depiction of a very simplified decision tree for diagnosing back pain. Now, let me say this is an academic example. You should not use this for medical advice in any way. So, and you could see the root, did the pain occur after a blow or a jolt? Answers are yes answers are to the right, no answers are to the left. That is how this decision tree is structured. And so if the user answers no, we get to, do you have a fever? No. Do you have persistent morning stiffness? No. See a doctor if pain persists. And you could see the other options as each of those levels of the tree progress down the path. Here we have the back pain analyzer class that really gets the application started. It prompts the user to get started, and it creates a new decision tree using the file input.txt. If you don't have this file, I'm going to give it to you, but if you don't have this file implemented correctly in the project, you're going to get null as your response. Then it calls the evaluate method. Here we have the input file for the decision tree project, which is called the back pain analyzer. And there is a discussion question about this particular input file and what the numbers before and after the contents of the nodes or decision points mean. 13 is pretty simple. Tells you that there are 13 nodes. What does 3, 7, 8, 4, 9, 10, 5, 11, 12, 1, 3, 4, 2, 5, 6, 0, 1, 2 mean? As you navigate this project, and it will be the most significant project to date, programming project to date in this class, you'll have to understand how those numbers are used to specify the nodes in this binary tree. Here is a UML diagram showing the relationship between the various classes and interfaces in this project. The bulk of the work that you're going to do to complete the decision tree project will be done in the linked binary tree class file. I want to say 100%. Yeah, I think it's 100%, but don't quote me on that. I probably shouldn't record it. But anyway, so now I'm going to move into a demonstration of the project in its completed form, which I did, to demonstrate to you how this thing works and what the requirements are of this 200-point project that is now in the timeline of Canvas and will be your most challenging project to date. I promise the demo is coming. One more slide to give you a little bit more background. We're going to be implementing a binary tree with links. The linked binary tree class, which is where you will do the majority, I think 100% of the work for the project for this module, which is a very significant project. You should take it very seriously and not wait till the last minute. Okay, that holds a reference to the root node. And the binary tree node class represents each node with links to a possible left and or a right. Okay, so this is a node with a link to a left and a right, just like we had the linked list, which had, no, not just like, similar to, expanded upon the linked list, which had the element at the node and a reference to the next node. This has possible left and or right child node linkages within each instance of the binary tree node. Okay, students, here is the most ambitious project you'll complete to date. This is the back pane analyzer, which is a decision tree. We've been discussing it for the past couple slides. I'm going to run my completed solution, which is representative of the requirements all completed from the rubric. So let's take a look at this. I've placed some breakpoints, and in my opinion, the best way to understand how this works is to see snapshots of the linked binary tree being built. So let me run this in debug mode. And so the first breakpoint I have is in the decision tree class, and we're going to take that file which we've talked about, you've seen the contents, and we're going to go from int I equals 0 to I less than number of nodes. There are 13 nodes. We got that from the first integer in the file, and we're going to we've created this list of linked binary trees that contain strings. Its name is node, and we're using the array list in java.util. And we're now going to add at each node, at each element, we're going to add a linked binary tree at each node, I should say. There's a lot of moving parts in this one, so stay with me. So, and if I go down to memory, you'll see here we have nodes, which is currently empty. It's an array list, and each indexed element is going to hold a linked binary tree. So I just walked over and I added to 0. Did the pane occur? Okay, added that first string as the root. Let's do it again. Okay, now I have in this array list, index 1 is another linked binary tree whose root is, do you have a fever? The element. No left, no right yet. We're going to get to that. So I'm going to blast through this, and it will iterate 13 times. And you can see, if we walk down through this, there's our root. You may have a sprain or strain, and you probably want to have a printout of the graphic depiction I had on one slide, 2 or 3 back, of this thing, the decision tree. Okay, so we're done, and we now have all these nodes. Okay, and they were taken in sequentially. And if you look at that file, you'll find the last string of 13 will be this one. You may have a muscle or nerve injury. Now we're going to go into building the actual linked binary tree. So we're going to get the root by the next int. So you'll see Okay. There's our first root, 3, and it's then going to have a left of 7 and a right of 8. Then we're going to go down here. We're going to nodes.set root is new linked binary tree string, nodes.getRoot, get root element, nodes.getLeft, nodes.getRight. So we're going to build a linked binary tree off of 3. Now if I look at 3 right now, left is null, right is null. Let's look at 3. The root, hey look, left and right are no longer null. Left is a binary tree node. The element in that binary tree node is C, doctor if pain persists. Right may have an inflammation of the joints. I'm doing your homework for you right now. If you're paying attention, doing your homework for you. So it will then walk down through the file using scan.hasNext, and it will specify the decision tree structure. Right? Right? Root 2, left 5, right 6, and now watch, let's look at 2. Here you go. It now has a left and a right. And guess what? Its left was already a root node for another linked binary tree. And now tree equals nodes dot get root. Look at that. There is our tree. Has a left, and the left has a left, and the left has a left, and there you go. And then evaluate just walks you through the interface for the decision tree. Did the pain occur after a blow? I'll just say yes. You have difficulty controlling your arms or legs, that would make this job pretty hard. Yes. Then there we go. We've gotten to the end of the decision tree. There were a lot of details in this. I had to do this recording 3 times because as I stepped through, I accidentally showed details of the assignment. It is a very challenging assignment. I will be here with you to help you, but this is what you should expect from this point on in the class. We are bringing to fruition one of the two most complex, in my opinion, complex classes that you'll take in our sequence. This and 240 are two very challenging courses. So I would pause this, go back and look at the rubric for the Chapter 19 Decision Tree project, and then play this again with the rubric, the requirements in the rubric, fresh in your mind, even printed or visible to you as you're walking through this. Students, that's the end of this module. A very significant leap in conceptual framework. It's our first nonlinear collection, and to say that the implementation of a binary tree is of a different level of complexity to the linear collections is an understatement. So I want you to take this material seriously. You're going to have to spend a massive amount of time on this content to really understand the underlying concepts of this nonlinear collection and be able to complete the 200-point programming project that I've assigned. It is not going to be easy. It is absolutely doable, and it is not beyond the scope of expectations for a course that's 6 contact hours in this degree. So thanks for watching this video. As always, I'm here to help you, but if you wait till the last minute, it's going to be very difficult because you're going to have questions that are going to be most likely beyond one iteration of emails or live sessions with me. Okay, thanks. Have a great day. I'm here for you. Ping me. Let me know how you're doing.